Welcome to Pre-Calculus. Today we will investigate finding side and angle measures of right triangles using the trigonometric ratios. We'll take a look at three examples. Our first example here is a right triangle where I have two of the side lengths. So of side AC, that's given as 2.3, and side BC, which is given as 6. And I'm looking to find the measure of angle B, which is marked here as angle theta. And I want to round to the nearest tenth. What I want to do first is identify what parts I have in terms of creating a trig ratio for this angle theta. So I'm just going to mark that this is where I'm beginning. And I just want to roughly say what these other sides are positionally with respect to theta. So the piece that is opposite theta is going to be this side AC. So I'm just going to identify that as the opposite side. And then I also see that the side that's adjacent to theta, BC, is given here as having the side length 6. And then I can mark the hypotenuse. I'll know it's the hypotenuse because it's the longest side of the triangle. It's also opposite the 90-degree angle. But for this question, I really am not going to consider the hypotenuse much because I don't know its measurement. The two parts that I do know measurements of are the opposite side and the adjacent side. So thinking about which trigonometric ratio I would define using opposite and adjacent, there's really two. I could use tangent. Let's remember the value of tangent. Tangent of theta is going to be opposite over adjacent. And then the second one is going to be cotangent. Remember, cotangent is basically the tangent ratio flipped over. So the other trig ratio that I could use in the setup for this question is cotangent. Again, adjacent over opposite. I'll go ahead and choose tangent since that's the first one I've got listed here. So the way I'm going to set this up, it's really going to look like the way we've defined tangent is tangent of theta equals, and I actually want to substitute in the length. So the opposite side here has a length of 2.3. The adjacent side has a length of 6. And that's my setup. I just want to create one of these trigonometric ratios from the angle provided and set up the ratio on the other side of the equation. Now for this question, I'm looking to find the measure of angle theta in degrees. I'll round it to the nearest tenth. And I need to think really, how do I cancel this tangent operation so that I can free theta? Well, in trigonometry, one of the functions that we have is an inverse function for all the trigonometric ratios. And that's what I want to apply here. So let me make some room on this right side. I'll just recreate that same fraction, 2.3 over 6, but I need space here because right now I'm going to apply the inverse tangent function. So I'll start over here on the left, and essentially the inverse of this original function is going to bump back for me just theta. And that's done what I wanted to on the left. Now on the right, this is actually an operation. The inverse of tangent of 2.3 over 6. And that right side is how I'm going to actually find the angle measure for theta here. So I want to take that to the calculator, tangent or inverse tangent of 2.3 over 6. And we want degrees. So as I head to the calculator, I need to make sure that it's set in degrees. So here I am on Desmos, and in Desmos, to make sure that that's the angle measure that we're using, I'm going to go to the graph settings. It's a wrench up there in the upper right. And I have two choices, radians or degrees. So for this question, I'm going to select degrees. Once the calculator is in the proper format, well, let me give the full screen view. I need to find the inverse tangent function. So that's under the keypad. So if the keypad's not showing, you just click the icon there, select the Functions tab, and then we're in trigonometry. And all these, the original trig functions are on the left column. There's the 6, and their inverses are in the middle column. So I'm just going to select inverse tangent, and then the values we had were going to be 2.3 for the opposite and 6 for the adjacent. So I'm just going to set that up as we had written it. And that gives me an angle measure of 20.97. So we'll take that back to our notes screen. And we want to round to the nearest tenth. So if it's 20.97, I would round that to 21.0 degrees. So we can use the trigonometric ratios specifically with the inverse trig ratios to find an angle measure if I have a couple of the side lengths in a right triangle. Let's take a look at a second example where we're looking not for an angle, but for a side. So notice on this example number 7, I'm looking for the measurement of side AC. I want to round to the nearest tenth. And the information I've provided is different. Notice now I have an angle measure at A, it's 31.2 degrees. And I know the measure of the hypotenuse is 7. So our approach is going to be slightly different here. I'm going to mark that as side C is 7. Side A we don't know. And then side B is what we're looking for. That's labeled X. So I have a similar strategy to the one that we employed in the first example, but here I need to look for a different trig ratio. So again, I need to say, here's my 31.2 degrees. I want to mark the part that I know and the part that I'm looking for. So the part that I know, this side C, is the hypotenuse. And remember, hypotenuse, you can identify it because it's the longest side in the right triangle. It's also opposite the 90. It doesn't actually touch the 90 degrees. It's opposite of it. The other piece that I am looking for is side B. That's labeled X there. And that's one of the legs. So it could either be opposite or adjacent. So the one that's opposite's not this one. Opposite's the far side B, C, which we've called A. And so what that means for me is that I've got to consider the adjacent side. That side B, length of X, is adjacent to angle 31.2. So I'm thinking about the trig ratios that I could define using the hypotenuse and the adjacent side. So like we saw in our first example, there are some options. My first option is the cosine function. So cosine of theta would be given as adjacent over the hypotenuse. And then I did have a second trigonometric identity ratio. Really the reciprocal of cosine, hypotenuse over adjacent, is secant. So I could use either of those two functions. I could use cosine, I could use secant, because they involve the adjacent and the hypotenuse sides. Since I've got cosine listed first, that's the one that I'll use. So I'm going to set this one up. Cosine of, now I actually have an angle measure here, so I'm going to substitute for theta 31.2 degrees. And I'm going to set that equal to the adjacent side, which is X, divided by the hypotenuse, which is given as 7. So our strategy here is different. To solve for a missing side length, I don't need to use an inverse trigonometric ratio because I already know the angle. And this cosine of 31.2 degrees is actually a fixed value. It's a number. So what I really need to do is isolate X here on the right side. And to do that, I just need to cancel the division by 7. So the way I'll cancel the 7 is by multiplying here on the right. It'll cancel. And then that 7 appears on the left as a factor multiplying times cosine 31.2 degrees. And that is solved for now. All I need to do is evaluate what is 7 times cosine 31.2 degrees. And we'll take it to our calculator. And we'll type it in as we wrote it. So 7 times, I'll find the cosine function over here under my functions tab. We've got the calculator way zoomed out. And then our angle again, let me check again, is 31.2 degrees. Before I finalize, I do want to make sure again that I'm in degrees. I hadn't changed it, but I'll make sure. So that's marked degrees. And so we are good to go. And that missing side length, the adjacent side, should have a length of 5.988. 5.988. So we'll head back to our note screen to finalize that value. We're rounding to the nearest 10, so 5.988 is going to round up to 6.0. So here we get the solution x equals 6.0. Let's take a look at one last example that is a word problem. So we've been looking at some of these examples where it is just given to us in an abstract way in a diagram. Here we want to actually consider a situation. So here I've got the roof of a house is to extend up 13.5 feet above the ceiling, which is 36 feet across, forming an isosceles triangle. And we want to find the length of one side of the roof. So I'm going to draw a diagram here of this roof. So I just have to imagine that I've got a house and I'm kind of looking at the roof from the side. So I'll try to make this a three-dimensional drawing. So there's our house. And really the part of the roof that we're considering here is this end portion, the portion that's making an isosceles triangle. Again, isosceles triangle means two of the legs or two of the sides are congruent. So I'm assuming that the actual parts of the roof are the same. And I need to mark some dimensions here. So if I were to put a vertical line to cut that end triangle into two, first of all, it would make a right triangle. And that part is 13.5 feet in length. Let me mark that. So from the ceiling, which would be here, up to the peak of the roof, it's 13.5 feet. I also know that the roof itself is 36 feet across. So the full length of the roof is 36 feet. And our task is to discover what's the length of one side of the roof. So these are the same lengths. Essentially, I want to find this length here. So it turns out probably we don't need trigonometric ratios at all here. I think we can do what we need to do with the Pythagorean theorem. So I want to just note that this is 36 feet from side to side. So from one side to the middle is just half of that length. So we're going to have a distance of 18 feet here for that lower half. So now I'm just in this left side right triangle, and I'm really looking for my hypotenuse C. So I'm going to pick up the Pythagorean theorem, a squared plus b squared equals c squared. And I know I'm looking for c squared, so I just write that. And then I want to substitute in values for a and b. Now I can call a or b interchangeably the two legs. So just selecting one of them, 13.5, I'll identify it as side A's length. And then 18 feet would be side B's length. So then I just need to multiply and add here. In fact, what I'll do is let me just set it up for the final solution. If I am looking for just side C and not C squared, I do need to take the square root. So that's going to cancel the square. And then the whole left side is going to get the square root. So that's what I need to input. It's the square root of 13.5 squared plus 18 squared. So we'll take that over to our calculator. And let's calculate the length of side C. So we'll put it all in as one expression. So the square root of 13.5 squared plus 18 squared. And that comes out to an exact value of 22.5 in length. We'll head back to our note screen to finalize that. So our solution here is C equals 22.5, and I do see my dimensions here are in feet. Well, thank you for joining for this investigation of using the Pythagorean theorem and trigonometric ratios to find missing angles and side lengths. See you soon.